22.2. Satellite motion. A satellite can be thought of as a special kind of projectile that is orbiting the Earth. If you can recall what you knew about projectile motion, a projectile is always an object that travels with a parabolic path. A parabola is curved, just like the shape of the orbit of a satellite. For satellites, the velocity of the projectile is so fast that its parabolic curvature matches the curve of the Earth. Every time the projectile curves as it falls, the Earth curves out from underneath it, and it just continues to curve around the Earth, eventually coming around and meeting itself on the other side from where it started. Slower projectiles will land on the Earth eventually, but if it's fast enough, it will curve and travel around the Earth. So a satellite is just a projectile that's going fast enough to orbit. Satellites are also special cases of circular motion, combined with the force of gravity. We're going to use three formulas in this lesson, three formulas that you've learned previously in the course. The first formula is the force of gravity formula from Newton's law of universal gravitation. This is Fg equals g, m1, m2, divided by the distance between the two masses squared. Remember, this distance is always to the center of the objects. Circular motion had two formulas, and either formula will be used in different situations. Fc equals m 4 pi squared r over t squared, where capital T is the period of the orbit, or Fc equals mv squared over r, where v is the speed of the orbit. We're going to number these formulas 1, 2, and 3 for easy use later. If we use the force of gravity formula, which is formula number 1, and the second formula for centripetal force, we can prove Kepler's third law. Whenever you combine formulas to create a new one, we call this deriving. So in this example, we're going to derive Kepler's third law. Remember, Kepler's third law is for an object in orbit around a planet or sun. We're going to use capital M for the planet or sun and little m for the object in orbit. So Fg equals g big M little m over r squared. And Fc is little m 4 pi squared r over t squared. There's some stuff we can cancel out. We see little m appears on both sides, so it cancels. We're going to move t squared to the top and r down to the bottom. This gives us t squared in the numerator and r cubed in the denominator. Moving gm gives the other side of the equation 4 pi squared over gm. This looks a lot like Kepler's third law. So much so that 4 pi squared over gm must be equal to Kepler's constant. So we can use the formula k equals 4 pi squared over gm for Kepler's constant, as long as we remember that m is the mass of the planet or sun that's being orbited. In this first example, we're going to use this formula we just derived to calculate the Kepler's constant for the sun. K equals 4 pi squared over gm. For the sun, this is 4 pi squared over 6.67 times 10 to the minus 11. This is the value for g, times 1.9891 times 10 to the 30, which is the mass of the Sun. K equals 2.97 times 10 to the minus 19 seconds squared per meters cubed. This is the value for Kepler's constant for the Sun. We can also combine the other circular motion formula with the force of gravity formula. So we'll look at force of gravity formula 1 and FC formula 3. And when we do this, we can derive a new formula for the speed of a satellite. So again, when we're doing this, we're going to use capital M to show the mass of a planet and little m to show the mass of the object that's doing the orbiting, or the mass of the satellite itself. So Fg equals Fc. This is formula 1 and 3 we're looking at this time. G, capital M, little m over r squared equals little m v squared over r. Again, we can do some canceling. M appears on both sides, and r is in the denominator on both sides, so we can cross out the squared. This gives us v equals the root of gm divided by r. This formula is for the speed of a satellite, and it's really interesting that the speed of a satellite only depends on the mass of the planet it's orbiting and how far it is from the planet. It doesn't depend in any way on the mass of the satellite itself. The satellite could be as big as the moon, or it could be as small as a little communication satellite. Its speed would be the same at that distance. So the speed of a satellite depends on the mass of the planet or sun it's orbiting, and on how far it is from the object's center. Be really careful with the r values when you're doing satellite motion, because r always goes to the center of the object, just like it did in universal gravitation. Example 2. Calculate the speed of a satellite orbiting Saturn at 6.43 times 10 to the 7 meters from the planet's center. Fc is mv squared over r, and Fg is m, little m, divided by r squared. Cancel out m and cancel out one of the r's to get v equals root gm over r. So this means for this satellite orbiting Saturn, 6.67 times 10 to the minus 11 is g. The mass of Saturn is 5.67 times 10 to the 26 kilograms divided by the radius to the planet's center, which is 6.43 times 10 to the 7 meters. This means a satellite at that speed above Saturn, height above Saturn, would be 2.43 times 10 to the 4 meters per second. Next, we're going to look at a special case of satellite motion. This is called geostationary orbit. Geostationary orbital distance is a special r value for a satellite. This r value allows the satellite to have the same speed as the period of the object it's orbiting, or as the speed of the planet or sun as it rotates. And you can see in this animation that this allows the satellite to hover above the same point on the planet as it orbits. Somebody looking up would see that satellite above them all the time. A satellite in geostationary orbit will appear to hover above the same point at all times. For Earth, geostationary orbit is about 3.6 times 10 to the 7 meters above the surface of the Earth. Again, be careful with your r values. The r values for the formula are always to the center of the object, although we often speak to each other as if we're speaking from the surface's perspective. For this example, I'm going to show you how to calculate the height above the Earth for geostationary orbit. So we use Fc equals Fg again. We're using formula 1 and 2. Gmm over r squared equals m 4 pi squared r over t squared. Again, m appears in the numerator on both sides, so it can cancel out. And since we're solving for r, we're going to move r to the numerator. We'll move r squared to the numerator of the opposite side, so r times r squared equals r cubed. So we get gmt squared over 4 pi squared equals r cubed. Solving for r means we get the cube root of gmt squared over 4 pi squared. Using this formula we've just derived, we can calculate the height for geostationary orbit for the Earth. The mass of the Earth is our m value. This is 5.98 times 10 to the 24 kilograms. And since we want to know the height for the period of the Earth, we use 24 hours, which is the time for rotation for the Earth, and this equals 86,400 seconds. So the radius equals cube root g, which is 6.67 times 10 to the minus 11, m, which is 5.98 times 10 to the 24, times r squared, which is 86,400 seconds squared, divided by 4 pi squared, and all this gets cube rooted. This gives us an r value of 4.23 times 10 to the 7 meters. But this isn't quite done, because this r value is the distance from the center of the Earth. Remembering that all our formulas that involve gravity and r always talked about the center of the planet. To get the height above the surface for geostationary orbit, we're going to call this r little g, or radius for geostationary orbit, we subtract from this r value the radius of the Earth. The radius of the Earth is 6.37 times 10 to the 6 meters. So our radius for geosynchronous orbit is 4.23 times 10 to the 7 minus the radius of the Earth, which gives us 3.59 times 10 to the 7 meters from the surface of the Earth, which is the value that's generally accepted to be the distance that will give us geostationary orbit.